Hi, everybody. So now we're going to do one more step and then put all the pieces together to get the proof of the fundamental theorem of classifying finite abelian groups. So now we're going to deal with the case. So far, we've completely analyzed abelian p groups. Now let's consider the case where the group doesn't have prime power order. But let's imagine that we have an abelian group which has order n times m, where n and m are relatively prime. They have greatest common divisor 1. And we're going to show that in that case, the group splits as a product gn cross gm, where gn is the subgroup consisting of elements whose order divide n, and gm is the subgroup of elements of order dividing m. And so the first thing to notice is that gn and gm are subgroups. So if a and b are in G, and the order of A divides n and the order of B divides n, then it's an abelian group. So if you take A plus B and you multiply it times n, you get NA plus NB, which is 0. So the order of A plus B must be a divisor of n. Here it's really crucial that the group be abelian, because if I wrote this multiplicatively, I'm using here the fact that AB to the n is A to the n, B to the n in an abelian group. So this is a place where this whole proof would fall apart if the group was not abelian. Anyway, so we have these two subgroups, and their intersection, if you take the elements whose order, and if you have something which is in both, that would mean that the order of H divides n, and the order of H divides m, which means that the order of H has to be 1. So we have these two subgroups. Their intersection is 1. To prove that we have an internal direct product, we have to show that they together generate the whole group. And this is Euclid's algorithm again. We can write AM plus BN equals 1. And then if we take any element G and G, we have, now I'll write it multiplicatively, that GAM plus BN is G to the M to the A, G to the N to the B, but it's equal to G, right? Because AM plus BN is 1. And G to the M is in Gn, because if you take G to the M and you raise it to the nth power, you get the identity, since anything to the mn power, which is the order of the group, is going to be the identity. And similarly, G to the n is in Gm, since G to the n to the m is the identity. And so we've shown that every element G is a sum, or in this case, a product of an element from Gn and an element from Gm. And that means that G is the internal direct product, and it's isomorphic to the product of these two things. So how do you finish the proof? Well, you take your finite abelian group G of order n, and you factor it into a product of prime powers. Now, by the previous result, used inductively, so for instance, you can factor n as P1 to the E1 times all the other stuff, use the previous problem, and you get that you can write G as GP1 to the E1. That is, everything whose order is power of P1, cross what's left. But then you can do the same thing for the next one. And these are distinct primes. And here, GPI to the EI, this is the collection of elements G in G for which the order of G is a power of just this one prime. And the previous result says that this is an isomorphism applied inductively. Each of these GP1, GPI to the EI, this is an abelian P group, right? Every element of this group has order dividing its order of power of P. So now we can use our result on abelian P groups to write this as G cross H, G1 cross H, where this is the element of maximal order, and H is the thing that we've worked out in that proof about the splitting of abelian P groups. But then this is still an abelian P group, so we can do this again. And we can keep doing this, and the order of this goes down until eventually it disappears. So we get that GPI is a product of cyclic P groups. And so if you put all this together, you've shown that your abelian group G, your finite abelian group, is a product of cyclic P groups. Let me conclude with a brief remark about finitely generated groups. So I, at the very beginning of this section, talked about what a finitely generated group was as opposed to a finite group. And I gave the example that a finitely generated group is like z to the n. So there is a better theorem, a stronger theorem about the classification of finitely generated abelian groups, and I'm just going to state it. Theorem. I'm not going to prove it. If G is a finitely generated, not finite, but finitely generated abelian group, then G is isomorphic to the product of a finite number of copies of the integers together with G tor, where G tor is the collection of elements in G whose order is finite, and G tor is a finite group. So you can apply the previous result. And one way to think about this is that if you have a finitely generated abelian group, it's a product of copies of Z and cyclic P groups. So if you want to think about, you can maybe think about Z to the K as a cyclic P group but there's no prime, but it's kind of an infinite. It is a cyclic group, but it's an infinite one. And this theorem, in some ways, is more of a theorem, in certain ways, more of a theorem in linear algebra than it is a theorem in just pure group theory. But at some point in your lives, you will probably come across a proof of this.